In this video, we're going to take a look at modeling with differentiation. So all we're looking to do in this video here is model real life situations by using differentiation. So what we've got here is an opening question. It's a very typical exam style question. The question says that the figure below shows a solid in the shape of a cuboid. Now we are given the dimensions for the shape. That's given as 4x centimeters by x centimeters by h centimeters. We're also told that the total surface area of the shape is given as 600 centimeters squared. So for the first part here, part A, again, like I said, really typical here. It says show that the volume of the shape v centimeters cubed is given by this equation here. Now the good thing about this is even if you can't show this, you can go on to answer part B and part C because you've got this equation here. Okay, so it's not all doom and gloom if you can't get part A, but obviously we do want to be able to get this first part here just for those marks. And kind of just to get into the flow of the question. Okay, so for part A then, let's think about this in two parts now. So we've got the information here for the total surface area. That's given as 600 centimeters squared. And we're also given this equation here for the volume of the shape. Okay, so let's start with the surface area. I'm just going to call this area here. So what do we know about the area? Well, we know that the area, let's call that A, that's equal to 600 centimeters squared. Okay, so we're going to write that A is equal to 600. Now, for the surface area here, or I should say the total surface area, that would be the sum of each individual face here, or the surface area for each individual face. Okay, now clearly, if I find the surface area for this face here, we need to double that because that's repeated on the back here. Same for the top of the cuboid here, it'll be repeated with the base, and same again here for this face at this back end here. So for the area then, A, that's going to be two lots here of the first three faces. Okay, these three faces here. So let's just calculate each individual face then. And because we've got the dimensions here, we can go on to do that. So for this face here, that's going to be 4x times by the height h. So that'll be 4xh there. We've got two lots of 4xh. This face here, this would be x times by h. So again, similar to this, it's just going to be xh though. We're going to get two lots of 4xh plus xh. And clearly we can simplify that, but we'll do that in a moment. And then finally for the last of the three faces here, this would be 4x times by x. That would be 4x squared. Okay, so plus 4x squared there. Like so. And we know that this is equal to 600. Okay, that's what we established here. That's what was given at the beginning of the question. Now from here, let's just simplify this part here. So the inside of the bracket, well, that will simplify to 5xh plus 4x squared. And rather than expanding that, by this 2 here on the outside, I'm just going to divide both sides by 2. I think that makes it just a little bit easier. So we're going to get 5xh plus 4x squared. And that is equal then to 300. Okay. And what I'm also going to do here now is rearrange this equation such that h is the subject. Okay. So if we do that here, I'm going to get that h is equal to 300 minus 4x squared. And that's all over 5x. If we divide both sides by 5x, we're going to get h equals this here. So all over 5x. And it becomes clear in a moment why we've rearranged here such that h is the subject. Now, that's the total surface area considered. What we now need to consider here is the volume of the shape. So for the volume then, well, this is V, and this is equal then to 4x times by x times by h. That's going to be 4x squared h, like so. Now we know that h is equal to 300 minus 4x squared all over 5x. So what I'm going to do now is substitute this here to my equation here for the volume. So V is equal, we've got 4x squared times by h here, which is 300 minus 4x squared over 5x. All over 5x. And then from here, we've done most of the hard work now. We just really need to simplify this and rearrange it such that it's in the correct form here. So we can cancel an x here and an x here. So now if we expand out here, get that v is equal. In fact, let me just rewrite this slightly. So I'm going to get 4x over 5 times by 300 minus 4x squared. Obviously, you can just go straight away into expanding here. I just want to make it a little bit clearer as to what's actually going on. So now if I expand here, I get that v is equal. I'm going to get 240x. So 240x there. Minus 16 over 5 x cubed. Okay, as required there. Okay. And there we have it. So that's the solution to part A. Like I said, you are given this usually though, just to help out. So even if you can't answer part A, you can still attempt part B and part C. Okay. So let's clear the screen then. That's part A answered. Let's just clear the screen though so we have enough room for part B. Now for part B then, it says find the value of x for which v is stationary. So for which v is stationary here, what that means then basically is we need to differentiate v here with respect to x and set that equal to 0 and then solve for x. Okay, that's just all the question's asking for, or that part is asking for. So we need the first derivative, so that's dv by dx. So you need to differentiate v here with respect to x. So should hopefully be nice and straightforward. 240x, that would give me 240. And then we've got minus 16 over 5 x cubed. So minus 16 over 5 times by 3. So it would give me minus 48 over 5. And then just subtract 1 from the power. So we get minus 48 over 5 x squared. Like so. So that's the first derivative. So now, like we said, we're going to set this equal to 0. So we've got 240 minus 48 over 5 x squared. And that is equal to 0. So now we take this over to the right hand side, then make it positive. We get 48 over 5 x squared. And that's equal to 240. We're going to times through by 5 and then divide by 48. So what I get here then is that x squared is equal to 25. Now clearly here, x can't be negative because x represents a length here. So clearly that can't be negative. So we just take the positive solution here. So therefore x equals 5. Okay. So x equal to 5. And that's just basically all we need for part B. That gives us the value of x for which b is stationary. Okay, so that's part B done. Then we move on to the very last part here, part C, which says calculate the maximum value for v, and it just basically says that we must justify that this is the maximum value using calculus. So, for the maximum value, that would basically be this value here for x, substituted into the formula here for the volume. Okay. So v is equal to 240 times by 5. And then we subtract here 16 over 5 times by 5 cubed. Like so. Well, 240 times by 5, that would give me 1,200. 16 over 5 times by 5 cubed, so that's 125. If we then divide that by 5, I get 25. So 16 times 25 here, that would give me minus 400. Like so. And then 1200 minus 400 here, that would give me 800 there. Okay, so I get 800 centimeters cubed there. So let me just double check everything's correct here. So 240 times by 5, 1200, perfect. 5 cubed is 125, divide that by 5, I get 25. that by 16 and we get 400. Yep, that's fine. And then obviously just do the difference here. So 1200 minus 400 gives us 800 there. And there we have it. So that's the maximum value for V. But we're not done here because we need to justify that this is the maximum value. And we do that by using calculus. So to justify that this is the maximum value, we now need the second derivative. So we need the second derivative here. Like so. So in this case here, now we're just going to differentiate this with respect to x again. The 205, that's a constant, so that'd be 0. Minus 48 over 5 times by 2, so that's going to be minus 96 over 5. Minus 96 over 5, just reduce the power by 1, so we get minus 96 over 5x there. So now what we need to do is substitute this value of x into my second derivative here, and clearly minus 96 over 5 times by 5, that's just going to give me minus 96 there. Okay, so when x equals 5, the second derivative then is equal to minus 96, which is clearly less than 0. Okay, and because this is less than 0, that means we have found the maximum value. So this justifies the maximum value. So justifies the maximum value. Okay. And there we have it. So like you can see, 3 parts there. Part A usually always given in this form here. So even if you can't show this, you can still go on to answer part B and part C. But there we have it. So that's the solution to B. And that's the solution to part C. And that gives us the solution there to question 1. So if we just take a look then at one more question here, we have question 2 where we have the figure below which shows a closed cylindrical container of radius r centimeters and height h centimeters. So for the first part here, again, you can see it's almost identical to the previous question, part A. It just says, given that the surface area of the cylindrical container is 400 pi centimeters squared, show that the volume of the cylindrical container, v centimeters cubed, is given by this equation here. Now, before we actually start part A here, I just want to make a quick point, and I didn't mention it for the previous question, but it is important here that it says that this is a closed cylindrical container. Okay. Sometimes you might have an open cylindrical container, and in that case, you have to account for that in terms of the surface area. So either the top would be missing or the bottom. Okay. In this case, it's a closed cylindrical container. It just makes our life a little bit easier. Okay. In terms of the previous question, it mentioned that it was solid. So again, the top or the bottom isn't missing, but we didn't mention it for the previous question, but I just want to make a note of that for this question here. So what do we know? Well, we know that the surface area of the cylindrical container is 400 pi centimeters squared. So again, we're going to think about this in 2 parts here. We have the surface area. Let's call this the area here. So we'll call that A. That is equal to 400 pi. Okay. Now, the formula then for the surface area for a cylinder should hopefully be nice and easy to remember then. So A is equal then to 2 pi RH plus 2 pi r squared. And this is equal then to 400 pi. So that's equal to 400 pi. So we can simplify this here. Straight away, we can just divide through both sides here by 2 pi. So I'm going to get RH plus r squared. And that is equal then to 200. So RH plus r squared is equal to 200. And just like we did for the previous question, I'm going to rearrange this here now such that h is the subject. In that case, then we get that h is equal to 200 minus r squared. And that's all over r there, sorry. So not RH, just r. So let me just erase that, sorry. There we go. So 200 minus r squared over r there. Okay. And again, it'll become clear in a moment why we've rearranged it such that h is the subject. So that's the surface area considered. Now let's consider the volume of the cylinder here. So for the volume then, V here, well, that's equal to pi r squared times by the length of the shape here, this prism, which would be h. So area of the cross section times by the length here, which is h. So we get pi r squared h. So pi r squared h there. Well, we know what h is here, or this rearranged form for h. That's 200 minus r squared over r. So we're going to substitute that into our formula or our equation for the volume. We've got pi r squared times by h, which is 200 minus r squared over r. And that's all over r, like so. And from here then, well, it's just a matter now of basically expanding, simplifying, and getting into this required form here. So again, I can cancel through by an r here. That becomes a power of 1. This r here will cancel. So what do we have here then? Well, I've got v is equal to pi r times by 200 minus r squared. So now if we expand this out here, I'm going to get 200 pi r. We get 200 pi r there. And then finally minus pi r cubed. Minus pi r cubed there. And notice now we've got the required form here. So as required, and there we have it. That is the solution to part A. Okay. So there we have it. So that's the solution to part A. And again, even if you can't show this, you can still go on to answer part B and part C because we've got the equation that we need here. Okay. So before we attempt part B here, let's just quickly clear the screen. Now for part B, it says find the value of r for which v is stationary. So again, looking for the stationary point here, so I need the first derivative. So here we need dv by dr in this case. So dv by dr. So just differentiate this here. So differentiate v with respect to r. I'm going to get 200 pi. So we get 200 pi there. And then this minus pi r cubed, if I differentiate that here, I get minus 3 pi r squared. Minus 3 pi r squared there. So that's the first derivative. If we're looking for the stationary point, I need to set this equal to 0. If I set this equal to 0, I can also add 3 pi r squared to both sides. We've got 3 pi r squared is equal to 200 pi. So straight away, we can divide both sides by pi here. So we get 3r squared is equal to 200. Now divide both sides by 3. So we get r squared is equal to 200 over 3. And then finally, we just want r here. And again, r must be a positive value. It represents a length here. So therefore, r is equal to the positive solution here then for this square root. So the square root of 200 over 3. Now, you don't have to, but what I'm going to do here is just simplify this. So this is the same as the square root of 200 over the square root of 3. Obviously, we can't do anything with the square root of 3, but the square root of 200, so if I do it over here, square root of 200, that's the same as the square root of 100 times the square root of 2. So clear that is 10 root 2. Okay, that's 10 root 2 over root 3. Okay, you don't ask for it in its simplified form, but we'll find this a little bit easier to work with in a moment for part C. Okay, so that's the solution to part B there. So that's the value of r for which v is stationary. And then finally for part C here, it just says show that the maximum value of the cylindrical container is equal to this here. So it might be a little bit small. So just in case you can't see this, this is 4000 pi root 2 over 3 root 3. We also need to justify that this is the maximum value using calculus. So the first thing that we need to do is substitute this here into our equation here for the volume. So V is equal, that's going to be 200 pi times by R here, which is 10 root 2 over root 3. I'll do this in a bracket here. So 10 root 2 over root 3. And then we subtract here pi R cubed. So minus, do this again in a bracket, pi times by R cubed. So R here is 10 root 2 over root 3. So pi times, this is 10 root 2 over root 3, all cubed. Okay. Now what makes this part here a little bit trickier than normal is because we need to get it into this exact form here. So rather than the previous question where it was just x equals 5, we just substitute and we get a value. It's a little bit more, there's a little bit more work involved basically for this part C here. But nothing too challenging. We should be able to get this, you know, without too much of a challenge, I think. So the first thing that I'm going to do here is, well, I've got 200 pi times 10 root 2 over root 3. So 200 pi times by 10, that's 2000 pi. I've got 2000 pi root 2, and that's all over root 3. Okay. We've then got minus here, so I've got pi times 10 root 2 over root 3, and this is all cubed. So let's just deal with this part here being cubed first. So basically, we think about this to begin with the numerator. Well, 10 cubed is 1000. So let's just do this over here. So I've got 10 root 2 over root 3. And this is all cubed. So 10 cubed is 1000. Root 2 cubed, well, that's root 2 times root 2, so that's 2. Then we times it by root 2 again. So 1000 times by 2, that's 2000. Then we times it by root 2. So the numerator here is 2000 root 2. Okay, I know I'm going on to the cylinder here, but it doesn't really matter too much. And then for the denominator here, that's going to be 3 root 3, because root 3 times root 3 is 3. Times it by root 3 again. So we get 3 root 3 there. Okay. So we subtract this here. Once we times it by the pi, obviously. So this is minus 2000 pi. So minus 2000 pi root 2. And that's all over 3 root 3. Okay. And notice here now we're looking pretty good. You know, it's 4000 pi root 2 over 3 root 3. That's what we need. I've got this here. So basically, we just need to figure out how we actually get to this final step here. And the way that we do that is by getting this over a common denominator. Okay. So if I get this over a common denominator here, what I'm going to get then is, well, I need to times this fraction here, both top and bottom, or both numerator and denominator, by 3. Okay. So what I'm going to get then is 6000 pi. We get 6000 pi root 2 minus 2000 pi root 2. And that's all over 3 root 3. It's all over 3 root 3. And then if we simplify this here, so 6000 pi root 2 minus 2000 pi root 2, that gives me 4000 pi root 2 over 3 root 3. Okay, so that's equal to 4000 pi root 2 there over 3 root 3 there. Okay, as required. Okay, like you can see, there was a little bit more work involved for that one rather than what we saw for the previous question. But again, nothing too challenging. This is A-level maths. It is supposed to be somewhat challenging. So there we have it. So that's the solution to, well, not quite the solution because we haven't justified yet. So let's just quickly do that. So we need to justify that this is the maximum value using calculus. So again, the fact that it's telling us to use calculus here just indicates that we need the second derivative. So the second derivative then, this would be d squared v over dr squared. So if we differentiate this here now, again with respect to r, well, 200 pi, that is a constant. So if you differentiate that, that's 0. We've then got minus 3 pi r squared. So if I differentiate that here with respect to r, I'm going to get minus 6 pi r there. So minus 6 pi r. Okay. Now, the value of r here is 10 root 2 over root 3, so that's positive. So when I times minus 6 pi by a positive number, that will be negative. Okay, because minus 6 pi is clearly negative, something by a positive, it doesn't matter what that positive is, it will still be negative. Okay, so when r equals 10 root 2, let me just clear that out a minute, sorry. So 10 root 2 over root 3, this here will be less than 0. Okay, so this will be less than 0. So therefore, we're running out of room a little bit here. Like you can see, it's a bit of a squash at the bottom, but this will be, this will justify that we have the maximum value. So therefore, maximum value. Okay. And there we have it. So like you can see, these questions are very kind of methodical. They usually follow the same kind of pattern. Part A to show that. Part B is usually just finding the value of r or the value of x, which v is stationary. In this case, it's v. And then part C is just finding the maximum or the minimum value. So there we have it. That's the solution to B. That's the solution to C. And that gives the solution there to the very last question, question 2. And that brings the end of this video on modeling with differentiation.